Okay, welcome to this sixth lecture. In order to motivate what I am going to do the next few lectures, let us look at a particular example. So, I take the cylinder, and on the other hand I also take C star, which is the set of complex numbers excepting 0, set of non-zero complex numbers, and then I can also look at delta star, which is the unit disk minus the origin. So this is the punctured unit disk, okay, where of course delta is the unit disk, namely it is a set of all complex numbers such that mod z is less than 1, okay. And then of course I can also consider an annulus delta r. So this is the set of all complex numbers z such that the modulus of z is less than 1 and it is greater than r, and here r is a real number, positive real number, positive fraction, okay, it is an element of 0 1, right. So I have basically the cylinder, I have the punctured plane, I have the punctured unit disk, and I have the annulus here, okay. And the point I am trying to say is that if you are going to look at these things as these objects as topological spaces, then they are all the same, they are all homeomorphic. For example, I can easily tell you how you can show that the cylinder and C star are homeomorphic. In fact, in the last lecture I told you that if you try to look at various structures of a Riemann surface on a cylinder, then I told you that if you take the set of isomorphism classes of Riemann surface structures on a cylinder such that and I am looking at Riemann surface structures that have been gotten by choosing a non-zero complex number and looking at the subgroup of automorphisms of the whole complex plane given by translations by that complex number, which was a subgroup that was isomorphic to z, and then I said you go C mod z, you go C mod the subgroup, then you get C mod z, which is essentially a cylinder. And I was also trying to tell you that the various Riemann surface structures that you get in this way, if you look at the isomorphism classes, set of isomorphism classes of such Riemann surfaces, then there is only one, and I told you that the standard representative is C star, and in order to show that C star is C mod z, I told you that is because of this because of the following C mod z is isomorphic to C star, that is by considering the exponential map. So you just send z to e power 2 pi I z, and this mapping will have for its kernel the integers, and therefore the source modulo the kernel thought of as an additive group is isomorphic to C star thought of as a multiplicative group, and this is the map, okay. So essentially I am just saying that C mod z is C star, and of course C mod z is also a cylinder because that is the way we got the Riemann surface structure on the cylinder, okay. So in fact one other way of looking at a homeomorphism between C star and the cylinder is as follows, as one of my students pointed out. So it is what you do is that you think of notice that if P1, so let me not use P1, let S2 be the real sphere, okay, and so you think of the real sphere as sitting here. So this is the, think of this as a unit circle on the xy plane. The axis of the cylinder is along the z axis, but don't confuse that z with the complex number z, and you have the unit sphere here, okay, and what you do is you have the origin here, okay. Now to every point on the cylinder you join the point to the origin by a line, and it will meet the sphere at a point, okay, and call that point as Q, okay. In this way you will get a map from the cylinder to the sphere, and the only point is that you will not get the north pole, because essentially there is no point on the cylinder which when joined to the origin is going to give you the north pole, and the same thing is going to happen to the south pole as well. So if I call the north pole as N and the south pole as S, so you get a map from the cylinder minus the north pole and the south pole, okay, and you can check that this is a homeomorphism. This is a homeomorphism, and this is another way of saying that the cylinder is actually C star, and the reason is because the sphere minus the north pole by the stereographic projection is just the complex plane, and the complex plane minus under the stereographic projection the south pole corresponds to the origin. So if you remove the origin from the complex plane, this is just C star. So let me put identify via stereographic projection with C star, okay. So this is a direct way of trying to realize that the cylinder and C star are homeomorphic, okay. Now let me tell you about the following theorem. So I'll recall this theorem fixing z not equal to 0, let me say in a non-zero complex number, okay. Let us consider the Riemann surface structure on the cylinder given by the quotient map C modulo n, so let me use z dot tz naught tz, which is a cylinder, and I have, so this is the quotient map which sends every, so what it will do is if you want, let me call this as or let me call the variable here, rather let me call this variable as omega, and let me call this t sub omega, okay. So you have the map, so this is the natural quotient map, and what is the quotient map? You send every complex number to its equivalence class under the action by the group of translations by integer multiples of omega. Okay, so what is this map? This is just you send z to the equivalence class containing z, namely which is the equivalence class is the set of all z plus n times omega, where n is an integer. So these are just translates of z by omega and integer multiples of omega, and this is one equivalence class which contains z, and this is the unique equivalence class which contains z, and this is the map. Okay, and when I say fixing omega not equal to 0, what we mean is that in writing down this map, maybe I should even put pi sub omega, because it depends on this choice of omega. The only condition on omega is that omega is non-zero. Okay, and what do I mean by consider the Riemann surface structure on the cylinder given by the quotient map? What I mean is, you make this into a Riemann surface. The way you make it into a Riemann surface is by actually getting for a point on the cylinder, you get a map in the other direction, which is a homeomorphism. Okay, namely the method was you take a point here, okay, and then you take a pre-image, for example take z. So a point here will be an equivalence class that will come from a point z. So you take a pre-image, take a small enough disk and make sure that the radius of the disk or the diameter of the disk is very small when compared to the modulus of this complex number. Okay, and then you take the image of that disk under this map. This mapping is an open mapping, and as a result you will get a neighbourhood of that point which is isomorphic to this disk, which is the disk around the pre-image, and this gives you a local coordinate chart, and this is how you get the Riemann surface structure. And once you get the Riemann surface structure, this map becomes a holomorphic map. Okay, so this is what we saw last time. So let me complete that sentence. Fixing omega not equal to 0 in C, let us consider the Riemann surface structure on the cylinder given by the quotient map being holomorphic so now the question is, if I vary omega, in principle I can get various Riemann surface structures on the cylinder which would depend on omega. Okay, and what is the, but of course all these structures will correspond to a quotient map like this, right? That is the only common thing, but as you change omega, you are getting different Riemann surfaces in principle. But what is it that the theorem says? The theorem says no matter how you change omega, if you consider them up to isomorphism, you get only one, and that one Riemann surface is going to be the Riemann surface structure on C star. See, mind you, C star is just an open subset of C. Okay, and any open subset of a Riemann surface is again a Riemann surface, because the only condition for surface to be a Riemann surface, an open subset of a surface is still a surface, it is still two dimensional. Okay, and it's still a Riemann surface because at every point in that surface I can still find local coordinate charts. Okay, all I have to do is take a coordinate chart with respect to the full surface and then intersect it with this open set. I will get a smaller coordinate chart. So every open subset of a Riemann surface is again a Riemann surface. In particular, C star is also a Riemann surface naturally, being an open subset of C. So C star inherits the Riemann surface structure from C. Okay, natural Riemann surface structure from C, and what I am saying is that this Riemann surface structure on C star, which is the sphere minus these 2 points by this identification, if I transfer it to the cylinder by this homeomorphism, I will get a Riemann surface structure on the cylinder, and I am saying it is that Riemann surface which is a representative for the set of isomorphism classes of Riemann surfaces arising in this way, which I say is a singleton. Okay, so let me write that down. The set of all let me call this as well, let me do something. I will call this cylinder as script C, and let me call this let me call the Riemann surface structure on the cylinder as C sub omega, okay, because in general you might expect it to depend on omega. Let me call it as C sub omega. Okay, so you take the set C sub omega where omega not equal to 0, omega is a complex number, take this set, okay, and then you go modulo the equivalence relation, which is isomorphism of Riemann surfaces. Okay, so mod isomorphism of Riemann surfaces, okay, then this is a singleton. This is a singleton. This is a singleton, and is identified and is represented by the Riemann surface C star. Okay, so this was the theorem that I wrote down last time, right? One of the theorems that I wrote down last time. Before I considered the case of a torus, I considered the case of a cylinder. Okay, now I want to state another theorem. So here is the theorem. Okay, so now let me look at all possible Riemann surface structures on the cylinder. Okay, take the cylinder. Let me look at all possible Riemann surface structures on the cylinder. Notice that when I do this, the cylinder is also C star topologically. Cylinder is also delta star. Okay, and there are also the annuli. Okay, they are all homeomorphic. Okay, and the point I want to make is that on delta star there is a natural Riemann surface structure, because delta star, the unit disk, the punctured unit disk, that is the unit disk minus the origin, is also an open subset of C, so it also has a Riemann surface structure. But notice that and similarly the an annulus like this, so this corresponds to an annulus like this. So you know it is the unit disk minus the origin, so I put a dot there. So this is no, so that was delta star, so that was delta, so let me draw it here, or let me just draw this as it is, rather let me draw it like this. So this is R, this is R, and this is 1. Okay, so this is my this is my annulus. Okay, and this is also a Riemann surface naturally, because I told you every open subset of a Riemann surface is also a Riemann surface. So this is an open subset of the complex plane. Mind you, the boundary circles are not included. Okay, it's the interior. You remove the boundary circles. Okay, the boundary circles will be included only if I put also less than or equal to, the inner circle is included only if I put less than or equal to here, and the outer circle is included only if I put less than or equal to there. So these boundary circles are not there. Okay, it's the interior of that is an open annulus, and that has a Riemann surface structure. Okay, now the amazing thing is that these are all homeomorphic. Topologically they are all homeomorphic to the cylinder, so they should all give you Riemann surface structures on the cylinder. Okay, but notice that C star and delta star, or for that matter C star and delta R, can never be biholomorphic. Okay, why? Because you see, if C star and delta star or C star and delta R is biholomorphic, that means you have a biholomorphic mapping from C star to delta star, or from C star to delta R, but it is impossible to have even a holomorphic map from C star to delta R or delta star, delta R or delta star. Why? Because once you have a holomorphic map from C star to delta R or delta star, it's a holomorphic map which in a neighbourhood of the origin is in a deleted neighbourhood of the origin is bounded, because the image is going to go into delta star and delta r, they are bounded. So you have a holomorphic map which is in a deleted neighbourhood of the point, namely the origin. It is a bounded map, okay, and Riemann's theorem on removable singularities will tell you that that will extend to a holomorphic map from C, okay, and if it extends to a holomorphic map from C to either delta star or delta r, you are going to get an entire function which is bounded, because it has extended from C star to C, it is going to become an entire function, and then since its image is going to lie in delta star or delta r, it is going to be a bounded entire function, and Liouville's theorem is now going to tell you that it has to be a constant. So what this tells you is that it is impossible to find a holomorphic map from C star to delta r to delta r or to delta star. So the moral of the story is delta star and delta r are certainly going to give you Riemann surface structures which are different from the natural Riemann surface structure on C star. So you are going to get some other non-isomorphic Riemann surface structures on the cylinder, okay, and then in fact the amazing thing is that no Riemann surface structure of the form that is there on delta r can be biholomorphic to the Riemann surface structure on delta star, and in fact delta, if you take delta r1 and delta r2 for different r's, they are all non-biholomorphic. So the amazing thing is you get a whole family of Riemann surface structures, possibility of Riemann surface structures on the cylinder, okay. So that is the next level of complication that you see in the theory, okay, and somehow the idea is how do you analyze the situation, okay, and the point is you analyze the situation by using some more techniques, namely you use the notion of what is called a fundamental group and the associated covering space, okay, and the techniques of fundamental group and covering spaces helps you to distinguish these Riemann surface structures. So let me write it down here. So the set of all possible Riemann surface structures, in fact I should say isomorphism classes, the set of isomorphism classes of all possible Riemann surface structures on the cylinder, okay, is is given by, so there is one structure on the cylinder which is the same as C star, okay. So what I will do is I will put C star here and I will put a square bracket saying that I am looking at all those Riemann surface structures on the cylinder which are biholomorphic, that is holomorphically isomorphic to C star. So that is what the square bracket means. It means take the equivalence class under the equivalence relation which is given by two Riemann surfaces being equivalent if there is a holomorphic isomorphism with an inverse which is also a holomorphic isomorphism, okay. Of course when I say holomorphic isomorphism, the inverse is automatically holomorphic and it is an isomorphism, and so this is one class. Then I will put this here, so this means disjoint union, okay. So you put disjoint union to say that something here does not occur anywhere else. So the other possibility is delta star, and again take the equivalence class, and then what I will get is this is the disjoint union of all these delta r's such that r is real fraction, real positive fraction, okay, and delta r1 is not biholomorphically isomorphic to delta R2 if R1 is not equal to R2. Okay. So you see, when you look at all possible Riemann surface structures on a cylinder, you notice that you are getting actually 3 types. 2 of them are just singletons, okay, and but the third one is a continuous family depending on one real parameter. Okay, this real parameter is a real number chosen in 0 1, but of course I could scale 0 1 to be the whole real line because that is not a problem. So essentially what happens is that if you look at isomorphism classes of Riemann surface structures in a cylinder, you get 3 families. These 2 are just trivial, but the third one depends on one parameter. Okay, so this is a theorem. Now the question is, how is it that one can go about proving such a theorem? So eventually we are going to prove all these theorems, but one needs the motivation for introducing certain more and more complicated tools. Okay, and we should have some motivation, otherwise there is no point in just giving definitions after definitions. Okay, so the key to all this is what is called the idea of a covering space. Okay, and the notion of a covering space is also connected with the notion of the fundamental group. So these are 2 notions that I have to explain. So the observation, so this is the observation. We do not have biholomorphic maps. I should not say even biholomorphic, we do not have even holomorphic maps. From C star C to delta star or C to delta R. Okay. So this reiterates what I was trying to say. You cannot have a holomorphic map from C to delta star, you cannot have a holomorphic map from C to any delta R, because if it is, you will get a bounded entire function, and of course I should say, when I say holomorphic maps I mean non-trivial maps. I am not worried about the constant maps, so I should say we do not have, let me say non-constant, that is very important. We do not have non-constant holomorphic maps from C to delta star or from C to delta R, but we do have a holomorphic map from C to, for example, C star or any Riemann surface structure which comes in this way. Okay, and so what is very special is this map, the existence of this map from C to this, and that is a non-trivial map, mind you, it is a surjective map, and that map expresses this Riemann surface as a quotient of the complex plane. Okay, so in some sense this is leading you to believe that delta star cannot be a holomorphic quotient of C, delta R cannot be a holomorphic quotient of C, but C star is, and every cylinder of every Riemann surface structure C sub omega that I have gotten here is of that type, and that should be the distinguishing feature. Okay, so it is very important to look at maps such as this, and these maps are called covering space maps. Okay, so let me write that down. However, we do have the holomorphic map, quotient map C to, if you want, C star or C to C sub, so that was script C sub calligraphic C sub omega, okay, which are covering maps. So, what is this? What is the speciality of these covering maps? So let me explain that. So, let us look at this map from C to C script C sub double omega, which is just C modulo the going modulo the translations by integral multiples of a single complex number omega. Okay. By the way, I should remark that n times t omega, which is t n omega, is actually, if you want to write it in multiplicative notation, it is t omega to the n, if you think of it as composition, okay, but additive notation is n times t omega, okay. So anyway, so look at this map. So if you look at this map and you look at this map and look at the way in which we got the Riemann surface structure. Let us go back and look at the way we got the Riemann surface structure. How did we get it? We did the following thing. So here was a cylinder. So here was a complex plane, and omega was this vector, and we drew these strips, and all these strips were of length mod omega, and omega was translation by omega mapped each of these strips into the other, okay, and we went modulo these translations, and the effect of that was we had to take a single strip and just identify the edges, giving us a cylinder, okay. So you got the cylinder here. So let me draw it here, okay. And given a point on the cylinder x, okay, what we did was we fixed a point z such that z goes to x under this map, okay, and we took a small enough neighbourhood of z, d, okay, small enough disk surrounding z, called that as d, and we took the image of that d under this map, which is pi sub omega. So this image here is pi sub omega of d, okay, and we noticed that because I had chosen the disk d small enough, the projection map restricted to that disk is a homeomorphism unto pi omega of d. So pi omega restricted to d from d to pi omega of d is a homeomorphism, and in fact we took the inverse of this homeomorphism to give us the local coordinate chart at the point x, which if you want is the center of pi omega of d, okay, or which is a point of pi omega of d, and this is how we got the coordinate charts. And the other thing that we noticed is that if you take pi inverse, if you take the inverse image of this under the whole map, what you would get is just translates the union of all translates of d, okay, with centers corresponding to the translates of z. So pi inverse of pi omega of d is just a union of let me say union over n belonging to z d plus translation d plus n omega, okay. So where of course by d plus n omega I mean the set of all complex numbers of the form z plus n omega where z belongs to d, okay, and mind you this union, because I chose d to be sufficiently small, this union is a disjoint union. So what is happening is that this is z and this is d, maybe if I draw strip here, then I will get the point here, this point will be z plus omega and this disk will be just d plus omega, okay. And similarly if I take the point here, this point would be z minus omega and this disk would be d minus omega, and so in this way you get a union of disks, they are all disjoint, and this is essentially the standard example of what a covering space is, okay. So let me make a definition. Let x and x tilde be topological spaces, okay. Assume x tilde are pathwise connected and locally pathwise connected, okay. So this is what I am writing in bracket is a technicality, and the importance of that technicality, when it has to be stressed I will stress it, but for the moment just assume this technicality, do not worry about it for the moment. So there are two topological spaces, okay, a map pi or let me call it as p from x tilde to x is called a covering map if p is continuous, surjective, and given x in x, given a point of x, small x of capital X, you are able to produce an open set surrounding x such that the inverse image of that open set under P, so I am thinking of this as x tilde, this as x, and I am thinking of this as P, okay, and you give me a point in x, small x in capital X, I should be able to find an open set such that the inverse image of this open set is a disjoint union of open sets, and the map P restricted to each of these open sets is a homeomorphism. So in fact what I should tell you here also, so let me also add this here, let me add that condition also here, that is another remark, if pi restricted to d plus let me take some n times omega from d plus n omega to pi omega, so this is pi sub omega of d plus n omega, which is the same as pi omega of d, is also a homeomorphism. Okay. In fact, I took pi from this disk D into its image here, but I could have as well taken any translate, because after all of them are going to be identified. Okay. So I want the same kind of thing to happen in a covering space situation. So let me write that down. So given x belonging to x, there exists an open set U containing x with pi inverse or p inverse of u, p inverse of u is disjoint union over some indexing set alpha v alpha in the space above being open, and pi or rather p restricted to V alpha from V alpha to U a homeomorphism. Is a homeomorphism. Okay. So the standard situation is that we have x tilde above, we have x below, we have a map which is surjective continuous. Given a point below, okay, I should be able to find a neighbourhood U such that the inverse image is a disjoint union of open sets above, such that when you restrict this map to each of those open sets, what you get is a homeomorphism with the open set below. Such an open set is called an admissible open set. It is called an admissible neighbourhood for the point x, and we say that it is a covering space if every point has an admissible open set. Okay, and so this is the standard covering space situation, right? And the other example that you can look at is that of the torus. Okay, so in the case of the torus, what we did was we fixed two complex numbers, okay, and we took the complex plane and went modulo the translations by integer multiples of these two complex numbers. Of course, we made the condition that the ratio of these two complex numbers is not real, because we wanted them as vectors to be linearly independent on the plane. Okay, so look at that situation. So we have let me call it as omega 1 omega 2 in C, well of course non-zero, and with omega 1 by omega 2 is not a real number. Okay, and then you have this map C to C mod you take the group which consists of translation by integer multiples of omega 1 plus translation by integer multiples of omega 2. Okay, so this group is isomorphic to Z cross Z. Okay, and then this gave you on, so there was the quotient is a torus, and it gave you a Riemann surface structure on the torus, and let us call that Riemann surface structure as omega 1 comma omega 2. Okay, and in this situation also, if you call this map as pi, of course you know you should be, this is pi which depends on omega 1 and omega 2. Okay, then you can check that this is also a covering map, this is also a covering space map in exactly the same way. In exactly the same way, the only thing is that in this case in the cylinder case, the plane was divided into strips of infinite length, translations of a single strip. Okay, but there the plane will be divided into a grid of parallelograms, and essentially all these parallelograms can be identified to one parallelogram, and then the only thing you will have to do is identify the opposing edges of the parallelogram, and that will give you a torus. Okay, so you can check that this is also a covering space. So the moral of the story is that the trying to get the Riemann surface structure on a torus, or trying to get the Riemann surface structure on a cylinder in this way as a quotient of the complex plane already involves a situation where there is natural occurrence of this idea of a covering space. Okay, and that is the motivation for looking at covering spaces in general. So the most general theorem that we have is that take any Riemann surface, just take any Riemann surface, then you can think of it as the quotient by a suitable covering space, and to make this covering space very special, namely to choose one special covering space among all covering spaces, there could be different covering spaces, okay. In this context let me tell you that this map factors through first going modulo just going modulo translations by integral multiples of omega 1 alone, okay, that would give you a cylinder, okay, and then there is going to be another quotient, okay. So I can do this in any order I want, and what it will tell you is that this covering space diagram can break down into two more covering spaces with the intermediate one being the cylinder, okay. So that means that you have two covering spaces for this, okay, and why is the covering space C special, and why is it different from the covering space that corresponds to the cylinder? The point is that C is simply connected whereas the cylinder is not, okay, and it happens that among all the covering spaces, if you look at covering spaces which are simply connected, you get a very special type of covering space that is called the universal covering space, and then it is an amazing theorem that any Riemann surface can be obtained as a quotient of a universal covering space which is a simply connected cover, okay. And the story does not stop there. What happens is, suppose you believe that theorem, okay. So given a Riemann surface, I have a covering space for it and that covering space is simply connected, okay. Now because of the covering space property, locally neighbourhoods there are homeomorphic to neighbourhoods here, okay. So what I can do is I can transport the Riemann surface structure on the Riemann surface to the covering space itself, and that will make the covering space into a Riemann surface, okay. And so what I would get is I would get a Riemann surface which is simply connected, but then my basic uniformization theorem says any simply connected Riemann surface has to either be the complex plane or the unit disk, which is the same as the upper half plane, or the Riemann sphere. So what is the upshot of all this? The upshot of all this is, take any Riemann surface, I have to obtain it, it is possible for me to obtain it as a quotient of either the Riemann sphere or the complex plane or the unit disk or the upper half plane, okay. So I am able to get a hold on the Riemann surfaces by being able to get them as quotients of these three basic Riemann surfaces which are simply connected, and that is what helps. And to carry out this process, therefore you need to get into a study of covering spaces, okay. So that is what I am going to do in the forthcoming lectures. And the other thing that I have to tell you is, where is it that the fundamental group is coming into the picture. So I'll define what the fundamental group is in a very formal way in the next lecture, but roughly let me tell you, the fundamental group is trying to look at trying to fix a point on a topological space and trying to look at loops starting at that point, continuous path starting at that point and ending at that point, and you declare two such loops to be one the same if one can be continuously deformed to the other, okay. So you do this and you can compose loops, okay, and in this way you can form a group which is called the fundamental group, okay. And this fundamental group shows up in the case when this covering is a universal covering, namely the fibers of this map, when x tilde is a universal covering of x, mind you I told you that x tilde is called a universal covering if it is simply connected, okay. And then by putting this condition of simply connectedness on x tilde, that makes x tilde unique in a certain way, which I will explain, okay. It singles x tilde out as a special covering space called the universal covering space, and then what happens if this is the special universal covering space for x, then the fundamental group of x shows up as the fibers of this map, okay, fibers of a map are just inverse images of single points, okay. So if you watch carefully in this map, the inverse image of a point is just a copy of z, it is all translates of so the inverse image of the point x is all translates of z by omega, integer translates of z by omega, and the set of all integer translates of z by omega is can be treated as z, okay. Similarly you take a point here, the inverse image of a point here will be a grid, it will be all integer translates by integer multiples of these two non-zero complex numbers. So the inverse image of this point is a set of dots, okay, going in a direction perpendicular, in a direction which is equal to the direction of omega, which is perpendicular to the direction of the strips, and there the inverse image of a point will give you a grid, okay. It will be actually the grid of parallelograms, if you take the vertices of the parallelograms, it is just that grid translated by a certain vector, okay. And what is that what is the grid of points? It is again z directs from z, okay. So in this case the inverse image of a point is just can be identified with a copy of z, in this case the inverse image of a point can be identified with a copy of z directs from z, but what is this z, what is the z directs from z? The fundamental group of the cylinder, which is the object below, is z, and that is what is showing up as a fiber, as the inverse image of a point. The fundamental group of the torus is z directs from is z cross z, and that is what is showing up as a fiber over a point. So what will happen is, when you take the universal covering space, the fundamental group of the base will show up as the fibers, not as a group, at least as a set, okay. So in some sense the universal covering space is gotten by putting as many copies of the fundamental group of x as there are points in x, putting together of course in a topological kind of way, okay. So the moral of the story is the fundamental group enters into the picture, okay, and that is the reason why the fundamental groups also have to be studied in this connection, okay. That's one point. Then the other point, notice that the fundamental group in this case, which is z, is also equal to this group, it is the group of translations by which we have gone modulo, okay. Look at this case, the fundamental group is z directs from z or z cross z, that is again the same as isomorphic to this group, which is the group of translations that we have gone modulo. So the moral of the story is, not only does the fundamental group show up set theoretically as a fiber over any point, it is also the group of automorphisms of the space above, going modulo which you get this space. So if P from x tilde to x is a universal covering space, then x is actually a quotient of x tilde by a certain group of automorphisms of x tilde, and that group of automorphisms of x tilde is nothing but the fundamental group of x. So the fundamental group shows up in two ways. It shows up as a fiber, which is the inverse image of any point, any single point, and it also shows up as the group of automorphisms of the covering space, the space on the top, modulo which if you go you get the space below, and that is exactly the quotient situation that helped us to give a Riemann surface structure on the cylinder or on the torus, okay. So the moral of the story is, therefore, if you understand the notion of covering space and the notion of fundamental and the notion of universal covering space, then you have a key to trying to reduce the study of Riemann surface structures just to studying such maps which are covering space maps, and that is the importance, okay. So and that is, in fact, that is a technique by which most of the theorems of this type are proved. In fact, all the theorems that I have told so far, except for the very fundamental theorem that the only simply connected Riemann surfaces are those which are either isomorphic to the in the non-compact case it is either the whole plane or the unit disk, which is the upper half plane, and the compact case it is just the Riemann sphere. But this is the most fundamental theorem. Proving this requires further techniques of analysis, for example, but if you assume this theorem, okay, and you assume this stuff about covering spaces, then more or less all other theorems can be proved. So which is what I am going to do in the next few lectures, okay. So all this is just a pep talk for you to await the definition and the intricacies that involve covering spaces and fundamental groups in the forthcoming lectures, okay. Right, so I will stop here.